swamp problem from Anderson and Woessner. All right. And remember, this problem looks something like this. We had a river up here. We had the Slate Mountains on one side, Slate Mountains on the other, and then at the down on this side, we had the green swamp. All right, and here's the river. And if we were to look sort of along a profile here from A to A prime, right? Oh, let's add some dimensions here. This was 10,000 meters, 10 kilometers, and this was 4,500 meters. And we got a well that we're going to put here. That's 1,500 meters, 2250, 2250. What else? All right, so if I look from A to A prime, so this is map, cross section. So 980 meters. Our land surface did something like this. This was 1020. This is 1,000. And the water level here is 1,000. And the water level here is 1,000. And this is green swamp. All right, and then we had constant recharge of a millimeter a day. The hydraulic conductivity here was 50 meters per day. Okay, I think we got most of what we need. So let's think about what packages we're going to use to turn this conceptual model into a numerical model. So our MODFLOW packages that we need to define. All right, and use. Okay, so the first thing we're going to do is domain and discretization. Okay, so that package is called the discretization package. And this is domain and discretization. All right. So this is the first package we're going to do. And that's just, you know, take our system, turn it into a series of aquifers and aquitars, tell it what size they are and how big the cells are. And we need to discretize the domain and discretize space and time. All right. So we're going to discretize space and time here. All right. The second thing. The second package we're going to use is the basic package. All right, and this is, you can think about this as our first boundary condition step, all right? And our initial condition. All right, so here, this is domain and discretization. Second is first set of BCs. This is constant head BCs or no flow BCs. And then the initial conditions, the initial head. All right, so the next package we're going to use is the layer property flow. LPF. And really what the LPF does is say, okay, MODFLOW, we're going to think of the world as these series of layers of thin aquifers and confining units. And we're going to define properties for each layer. And so you can think about this as sort of telling it it tells it a little bit about the PDE, and it tells it about parameterization. All right. So this is the PDE. How are we going to think about the aquifer? But most importantly, how are we going to parameterize it? All right. And here we're going to tell it about the type of aquifer. All right. And when we do that, we're going to tell it the PDE to solve. Okay, so layer package flow, PDE, parameterization for well package. All right, we're going to have a well, so we need to use the well package. All right, you can think about this as setting up the source sink. All right, and so this affects the PDE. It affects the PDE and sort of the boundary conditions. All right. We're going to use the recharge. We have recharge, so we're going to use the recharge package. All right, and this is the second boundary condition step. And this is for a specific boundary condition, and that's recharge. All right, so it actually also affects that doesn't really affect the boundary or the partial differential equation, but it does add our constant flux boundary condition or our specified flux. All right, the other one we're going to use is output control. All right, and this will be how often and what do we write? And what do we write to file? All right, and this is instructions for MODFLOW. All right, this is not really part of our conceptual model. This is just instructions for MODFLOW to tell them or to tell MODFLOW, the model, when to output. Now we're going to construct our output control knowing, what the problem is we want to solve. Okay, and then also we're going to use a solver package. We're going to use the precondition conjugate gradient package. conjugate gradient package, PCG. And this is solver. All right, remember solver for H equals the A inverse H, T plus 1 equals the H inverse T. All right, so this tells me something about this A inverse. And again, this is instructions for MODFLOW and the solution method. Okay, so here's what we're gonna, these are the packages we're gonna use. This is how we're gonna take all the parts of our conceptual model, all the ingredients for our BVP, and implement them numerically in MODFLOW.